definition, let me give you an example. It's a result of Bianconi. So consider the real exponential field and the sine function restricted to a compact interval. Well, then this function, the restricted sine function, is not definable. For no interval is this function definable with parameters in Rx. So geometrically, what this means is that you cannot obtain any arc of sine, or the sine function, from the following geometric construction. You start with zero sets and positivity sets of exponential polynomials, and you close under finite unions and intersections, taking complements and projections. A converse to this result, well, the exponential function, as any continuous function, and indeed any open subset of R to the n, is definable in R sine, because the ring Z is definable in R sine, so you can code any countable union of balls with rational center and rational radius. So this is not really an interesting converse if you're looking for a geometric characterization. A better converse is the following. No restriction of the exponential function to any compact interval is definable in the restricted structure where I put just a restriction of the sine function to a compact interval. So this is a better question and a better answer, because there we stay in a realm of tane geometry and ominimal structures. So this will be the topic of this talk. So I will say that the exponential function and the sine function are not locally interdefinable. So let me put this another way. If we identify C and R square, then with the exponential function and the restricted sine function, we define over the reals the complex exponentiation restricted to the strip where the imaginary part is bounded. So another way of stating Bianconi's result, or part of Bianconi's result, is to say that complex exponentiation is not definable, not even locally, from real exponentiation. So for many most interesting holomorphic functions, for example, periodic functions, if we decide for some reason, as Bianconi did, to separate the real and imaginary part, then, and we want to keep a geometric interpretation, we want to stay within a tane geometric setting, the notion of real definability of holomorphic functions that we'll have to look at will have to be local. So, but why would one want to do that, separate the real and imaginary parts? So, three reasons. So the first reason, the most obvious one probably for the people in this audience, is that the model theory of interesting holomorphic functions is less well understood than that of at least the restrictions of their real and imaginary parts, where we have actually a very rich theory of definable complex analysis and powerful tools. Another reason is the following. So saying that something is locally definable, well, a function is locally definable from another function means that I take the graph and then I perform some geometric constructions, intersections, unions, projections, taking complements, and I end up with another set which happens to be the graph of a holomorphic functions locally. It would be certainly nicer and more informative to say, well, I start with a bunch of functions and I perform a certain number of natural operations, for example, well, sum and products, derivation, differentiation, taking partial derivatives, composition. And then I end up with my locally definable function. And this is particularly interesting in a complex case, since what we've done is the first thing we do is that we separate the real and imaginary parts, and then we do some constructions, and then we patch them back together. So it would be nice to know that there is a sequence, a finite sequence of complex operations that makes me go from one function to the one which is locally definable for my first function. And then the third reason, which is a more geometric reason, is that, well, we certainly get more powerful tools and more information about how to describe explicitly, locally, sets definable via real analytic functions if we can access definably their holomorphic extensions. So what I'm thinking of is the Weierstrass preparation theorem, which is a complex theorem and which in general we don't have access to definably. So the interplay between the real and imaginary part can be interesting also to get information about real analytic functions. So the material I will cover in this talk is joint work with several people in different combinations. So we'll cover, hopefully, material coming from these 3 papers. So in the first one, we consider a question which is very much in the spirit of Bianconi's result. We ask a similar question, but about Weierstrass elliptic functions. And I will show what kind of results one gets, what kind of proofs, methods we use, and what kind of applications one might think of would follow from that results. The other 2 papers are more about my second motivation, that is finding a way of characterizing local definability in terms of operations on functions. So in the first paper is about the complex case, and the second paper is more about the second paper is about the real case, where we get some partial answers in the complex case and a more total picture, global picture in a third paper. So now, definitions. So let K be R or C. Definable throughout this talk will mean definable with parameters. So given a real or complex analytic function defined on an open set, if delta is an open relatively compact box with rational corners, we call the restriction to delta of G a proper restriction of G. And if F is a collection of real or complex analytic functions, so I don't know if this is clear, I will treat separately the real and the complex case. So you fix K, which is either R or C for the slide. So if you have a collection of analytic functions defined on open sets, then I call F restricted the collections of all proper restrictions of functions in F, and R sub F restriction, the expansion of the real field by all proper restrictions of the functions in F. So, yeah, at least for this definition, so everything actually lives in R sub n. And I will say that G, a real or complex analytic function, is locally definable from F a collection of analytic functions if all the proper restrictions of G are definable in this structure R sub F restricted. So for this talk, I will say that two collections of functions, of holomorphic or real analytic functions, are not locally interdefinable if no f from big F is locally definable from G, and no G from big G is locally definable from big F. So a first remark, what the simplest example of locally definable functions. Well, if I start with an analytic function f, then over the complex numbers, the Schwarz reflection f bar of z bar and the partial derivatives are clearly locally definable from f, well, the first because conjugation is locally definable, and the second just by the epsilon delta definition. So here's an example of functions which are easily seen to be locally definable from f, and also it is quite clear, I mean, they're defined in a way, I'm not saying what I'm doing to the graph, I am describing an operation on function. Okay, so now in the spirit of the result of Bianconi that I mentioned, we will consider the exponential map of the following complex projective elliptic curve. So let me fix some notation. So lambda will be a lattice in C generated by two R linearly independent complex numbers, omega 1 and omega 2. And the Weierstrass P function with respect to lambda is this meromorphic function. So it's holomorphic outside of lambda. It's periodic with respect to lambda. So I'm describing the properties that we will need to know about this function. And it is differentially algebraic. This is the differential equation satisfied by P, where the coefficients have appropriate expressions in terms of the lattice. And the link between the P function and the elliptic curve, the equation of which I wrote on top of my slide, is this function exponential with respect to E, which is a universal covering map and which is expressed in terms of P and P prime. So our question will be, what can we say about the local interdefinability of complex exponentiation and a P function, or what can we say about the interdefinability of two P functions? And here's the result. So I will do it gradually. First, easy statement, no P function is locally interdefinable with complex exponentiation. And if I take two P functions, P1 and P2, then they are locally interdefinable if and only if I can obtain one from the other by two operations, isogeny and Schwarz reflection. So if and only if P2 is isogenous to either P1 or the Schwarz reflection of P1. More generally, if F1 and F2 are two disjoint sets of P functions, then a P function from F2 is locally definable from F1 and complex exponentiation if and only if there exists a P tilde Weierstrass P functions in F1 such that P is isogenous to either P tilde or its Schwarz reflection. So this is indeed an equivalence relation. I will say that P and P tilde are ISR equivalent, isogeny Schwarz reflection equivalent. Furthermore, well, suppose that all the p functions in my two collections, if I take the union of the two collections, all the functions are pairwise non-ISR equivalent, and let X be a subset of R to the n. So I consider two structures, R1, which is the expansion of the real field by all proper restrictions of functions in F1 union exponentiation, and R2, where I make the same constructions from F2. Then X is definable in both structures if and only if X is semi-algebraic. So the key point to understand both the statement, the meaning of the statement, and part of the proof is really Axe's theorem, which says that if I take a collection of Q linearly independent power series without constant term, and then I consider the set of these power series and their exponentials, then the transcendence degree over C of this collection of functions is at least m plus 1, where m is the size of the set of power series. So there is a version for, of this theorem which involves exponentiation and finally many pairwise non-isogenous p functions applied to linearly independent sets. I should have said sets. For every function, I have a set of linearly independent power series without constant term. I will give the statement, the precise statement later, but for now, just know that it is a version of Axe's theorem for p functions and the exponential function. So what theorem 1 says, one of the things that it says, is that not only are all these functions algebraically independent, as can be seen from Axe's theorem, but they're also pairwise orthogonal with respect to local definability. They're somehow independent with respect to local definability. This is one way of interpreting theorem 1. So before talking about the proof, I will show how this type of result could be used. So it could be used to prove that certain functions are transcendental. So here is an example. Let f be the set of all p functions, and then little f, let little f be a transcendental real analytic function which is locally definable in Rf, locally definable from f, I mean. Then the function which I obtain from f by composing with log on the right and with exp on the left is transcendental. Why? Otherwise it is algebraic, and then f is obtained by composition of log and exp with an algebraic function, so f would be definable not only in locally definable in Rf, but also definable in Rexp. Hence, by theorem 1, f would be algebraic, but f was transcendental. So just as an example, this result can be used as a counting application. So let f be as above, and let ph be the height function over the rational. So the height of a rational expressed as a reduced fraction is the max of the absolute value of numerator and denominator. Well, then we have this, Pila-Wilke-like result, Pila-Wilke sounding like result. So there exist constants c and gamma, depending only on f, such that the set of log of rational points that lie on a graph of f, the density of the set, the density of this kind of points, these log of rational points on the graph, has a growth of type a power of log. So how do you do that? Well, it's enough to count, it's the same thing as counting the pairs of rational numbers on a graph of G as above. Now it's not difficult to see that G is definable in some model complete reduct R or R pfaff, and then we apply a result, a counting result by Jones and Thomas for counting rational points on transcendental curves, definable in this kind of redux of R pfaff. Okay, so now I'll talk about the proof of theorem 1. So I'll do it in 2 steps. 3 steps, okay. Well, first, let me introduce the main ingredients. So there's an easy direction. We have already noticed that Schwarz reflection is a locally definable operation. In particular, for p functions, the Schwarz reflection of a p function is a p function relative to the conjugate to the conjugate lattice. A second remark: if the 2 lattices are homothetic, then it's easy to find explicitly an expression of p2 in terms of p1, just using the parameter alpha. And if lambda 1 is contained in lambda 2, then in particular p2 is periodic with respect to lambda 1, and a general result about elliptic functions periodic to a certain lattice says that then p2 must be a rational combination of p1 and p1 prime. So putting everything together, if p2 is isogeny Schwarz reflection equivalent to p1, then p2 is locally definable from p1, should be from p1, not p2. So one direction is easy. For the other direction, so, okay, fix a collection of holomorphic functions, not necessarily p functions, and another function which is a holomorphic function which is not in F. We have already observed that Schwarz reflection and taking derivatives preserve local definability. Here are 2 other examples of operations, natural operations that preserve local definability, which are composition and extracting implicit functions. So the question is, once we have noticed this, do we have a complete characterization? So are these 4 operations that I mentioned enough to characterize local definability? Our first ingredient is a theorem of Wellkeys that says the following. So let Z0 be suitably generic. I will say more about this later. Then G is locally definable from F in a neighborhood of Z0 if and only if G is indeed obtained from functions in F and the polynomials by finitely many applications of these 4 operations that I mentioned: Schwarz reflection, differentiation, composition, and extracting implicit functions. So this will be ingredient 1 in our proof. And ingredient 2 is the Axe-type result for p functions that I was talking about before, and that I will state a little bit more precisely here. So I take n functions. Each function is either exponentiation or a p function, and the the p functions are pairwise non-isogynous. Let Ki be the CM field of Fi. You only need to know that it's either Q or a quadratic extension of Q. And then you take for every I, for every function, you take a finite collection of Ki linearly independent set of power series without constant term. Then, exactly as in a statement of Axe's theorem, the transcendence degree of all these power series and of the functions each applied to its own bunch of power series is at least the sum of the sizes of the sets of power series plus 1. Okay, so second step, I will first talk about the proof of the theorem in an easy case, which is, I think, quite not so difficult to grasp. And then I will talk about the general case, and that's a bit more rough. So the easy case is the following. We consider two non-isogynous p functions, and to make my life easier, well, part of the easy case is the fact that each of them is equal to its own Schwarz reflection. And now suppose for a contradiction that P2 is locally definable from P1. So in this special situation, Wellkeys' theorem was about just a bunch of holomorphic functions. But in this special situation, where we have all the properties of the p functions, in particular differential algebraicity and the group structure on the elliptic curve, Wellkeys' theorem that said that P2 is obtained from P1 by differentiation, composition, and implicit function, here has a stronger statement, a more explicit statement, a more interesting statement. The following: P2 is generically implicitly definable from P1, which means the following thing, that around a suitably chosen Z0, there is an M, and there is an m plus 1 tuple of holomorphic functions, G, such that Z is one of the coordinates and P2 is another coordinate, and such that the 2m plus 2 tuple of all the coordinates of G and P1 applied to each coordinate of G satisfies a non-singular system of m polynomial equations. So in particular, this gives an upper bound on the transcendence degree of the coordinates of G and P1 applied to the coordinates of G, well, number of variables minus number of equations, that gives m plus 2. But Axe's theorem, in a statement by Brownell and Kubota that I stated in the previous slides, applied to the two functions P1 and P2. And for P1, I consider the set of holomorphic functions which are the coordinates of G, and for Phi2, I just consider Z. If you look at the statement, what it says, it actually says that the same 2m plus 2 tuple of functions has transcendence degree at least m plus 3, a contradiction. So Wellkeys' theorem in this specific situation where we have a group structure gives an upper bound on the transcendence degree of a certain tuple of functions, and Axe's theorem gives a lower bound, and the two bounds are incompatible. Okay, so ready for the general case. So please, if you get lost in the general case, be reassured I'll go back to more understandable things at the end of the proof of the theorem. So we need a definition. given a set of f of holomorphic functions, local definability from f induces a closure operator, which I call the holomorphic closure with respect to f, on subsets of C. The following operator, given a subset of C and a complex number B, I say that B is in the holomorphic closure of A if and only if there exists a holomorphic function G which is locally zero definable without parameters from F, and the tuple A in a domain of G such that B is equal to G of A. So what Wellkeys theorem actually says is that this closure operator is a pre-geometry. So in particular, there is a notion of dimension attached to it, which I will call dim sub f. And it also says that this closure operator, that a priori talks about functions locally definable from other functions, can be expressed in terms of suitable derivations on C. So this is particularly relevant to us for two reasons. Well, first of all, dealing with derivations makes computations easier. They're essentially, well, computations about dimension of vector spaces. But more to the point, we can apply the differential version of Axe's theorem, thanks to this formulation of what local definability means. Now, if f is a set of holomorphic function and g is another holomorphic function, then clearly, if g is locally definable from f with parameters in a certain set C0, then for all a in the domain of g, g of a belongs to the holomorphic closure of a and the parameters. So in particular, the dimension, the dim f of the tuple a g of a over C0 is 0. And there's a partial converse to this. If we're dealing with the algebraic case, no functions in my, no transcendental functions in my collection F, then actually having dimension 0 implies that G is algebraic, that is, that G is locally definable from the empty set, that is, G is algebraic. Okay, so here's the first step of the proof. We take two finite sets of P functions which have empty intersection. So we have F1 and F2, the intersection, I will call it F0, and it is empty. And the union, I take the union and I also throw in the exponential function, and I will call this F3. And I will suppose that any two P functions in this collection are not isogeny Schwarz refraction equivalent. Then I take a function g, which is holomorphic and locally definable separately from f1 and exponentiation, and locally definable from f2. Well, in particular, it is also definable from the union f3. And what we will prove, the first step is to prove that G is algebraic. So with this notation that I have introduced above, what I'm saying, it is enough to prove that if the tuple AG of A has dimension 0 for I equals to 1, 2, 3, then it has dimension 0 for I equals to 0. So this is the statement, again, of step 1, what we have to prove. Okay, so we introduce a pre-dimension function after Ruszowski in an incarnation in the spirit of Boris's and Jonathan's work. So consider a countable subfield C0 in which we are going to throw in all the parameters and in which we are going to hide number theoretic questions. And suppose that it is closed with respect to the pre-geometries that I'm considering. Let B be a tuple, and for a function in my collection, I will denote by kf the CM field of f. Again, this is either Q or a quadratic extension of Q. Then we define for every I, going from 0 to 3, we define a pre-dimension function delta I. So delta I of B over C0 is the transcendence degree of B and the collection of all the functions applied to all the coordinates of the tuple B over C0 minus the linear dimension over Kf, and I do this for all the functions, so I take the sum of B over C0. So what does this measure? So for example, to talk about something you're probably more familiar with, Shanlow's conjecture says that for all B, delta exp of B over Q, or over the empty set, as you wish, is non-negative. So what we do is we prove step 1 by showing, using the two ingredients, Wellkeys theorem and Axis theorem, that for all the delta i's, well, we have an X type statement, so delta I over C0 is non-negative. Then, well, and here I'm cheating a little bit, we can reduce to the situation in which this delta I, the delta I of the tuple I'm interested in, coincides with the dimension of the tuple I'm interested in. So this is what, so when I was talking about Wellkeys theorem expressing local definability in terms of derivation, here where it comes in, so I have a dimension, I want to measure a dimension which is expressed in terms of local definability, and I managed to express this in terms of the delta function, for which computations are a lot easier. They're algebraic and linear computations, and actually they're even easier than one might expect, in the sense that the following modularity result holds. Delta of the union is equal to delta 1 plus delta 2 minus delta of the intersection. So remember that I knew that delta 1, 2, 3 of my tuple were 0, and I wanted to prove that delta 0 is 0. Well, that's done. So this was step 1. Any holomorphic function which is locally definable from two disjoint sets of functions as, which are pairwise non-equivalent must be algebraic. But to get the full statement, I need to do something, a further step. So let X be a subset of R to the n, which is definable in both structures, and I want to prove that X is semi-algebraic. So this is done by minimal considerations. There are essentially two steps. The first step is to show that X is definable in both structures by the same real analytic functions. So we may suppose that X is an analytic cell defined by analytic functions which are definable in both structures. Hence, we would like to apply the first part of the theorem to the functions defining f, and we can. Why? Why can we? Well, because of this second step that says that every definable real analytic function, definable in these two structures, is almost everywhere the restriction to the reals of a locally definable holomorphic functions to which we can apply step 1. So this concludes the proof of theorem 1. So let's get to the other questions. Let's get back to Wellkeys theorem. So Wellkeys theorem gives a characterization of local definability around generic points. So now you've seen pre-geometries coming in, you understand what generic is about. There's also, so this is Wellkeys theorem is a complex holomorphic theorem. There is also a real version which is much easier, which is a consequence of Gabrielov's theorem, also around generic points. So it is natural to ask what happens if we remove the genericity hypothesis. So some considerations, very vague. Well, being in generic position means essentially being transversal. So if we remove the genericity hypothesis, one might expect that some resolution of singularities might be needed. Now, strange phenomena may occur during resolution, and indeed they do. So the answer is no, the above operations are not enough to describe all locally definable analytic functions in the neighborhood of a non-generic point. So this characterization works around generic points. Around non-generic points, these 4 operations, Schwarz reflection, differentiation, composition, and extracting implicit functions, will not be enough. And we show that there are at least 3 further operations that are needed in order to capture local definability around non-generic points. So these new operations are monomial division, theoremification, and blowdowns, and they come indeed from resolution of singularities. So I'll say something about that. First, again, the easy case. So an example of what happens in theorem 2, that is an example of a function which is locally definable from another function, but which cannot be obtained by the 4 operations in Wellkeys theorem. So as a collection, a basic collection of functions, I take complex exponentiation, and then I consider the function g, which is defined as e to the z minus 1 over z if z is non-zero and 1 otherwise. Well, then g is clearly locally definable from x. If Wellkeys theorem applies in a neighborhood of 0, which is a non-generic point, then, as we did in the proof of the easy case, in the proof of theorem 1 in the easy case, we can show that g is a coordinate of an n-tuple of holomorphic functions, which are solution of a non-singular system of n-1 exponential polynomial equations. So using this and the further equation that says that g and exp are algebraically dependent implies that n is an upper bound on the transcendence degree of the tuple g and of their exponentials. Exactly the same trick we used before. Now, Axe's theorem, in his more basic and classical statement, implies that the transcendence degree of this same tuple is at least n plus 1, a contradiction. So if we want to describe g, the function g, then we need a new operation, which I will call monomial division. For the other two operations, the definitions and the examples are more involved and less explicit. In particular, we do not have an example with complex exponentiation. So we'll just say a few words about this. So to create the other two examples, we need a notion, due to Olivier Le Gall, of strongly transcendental function, which is actually similar and connected to a function, a notion that Boris considered a long time ago and called them generic functions with derivatives. So these are functions satisfying very few relations. I will be vague. In particular, they're not differentially algebraic. So the idea is that we find a strongly transcendental holomorphic function. We have to show that it exists. Well, it exists. There's plenty of them. We don't know any of them explicitly, but we know that they exist, such that G is locally definable in a neighborhood of 0 from G of Z squared, which I'll call F, but which cannot be obtained from F by the previous operations. Hence, we need a new operation composing with square roots, with third roots, composing with nth roots. I will call this deramification. But we're not done yet, because we can find a strongly transcendental function in two variables, which is locally definable in a neighborhood of 0 from its blow-up, which is a collection that I wrote there in coordinates, but which cannot be obtained from this collection by the previous operations. Hence, a new operation is needed, blowdowns. So it is easy to see that these operations, well, they come from resolution of singularities. They are applied at singularities, so they are only needed at non-generic points. So we're not contradicting Wellkeys theorem. So of course, the next question is, is our list of operation complete now? Can we describe every locally definable holomorphic functions by applying finitely many of these operations to the collections of the functions we started with? And we don't know in a complex case. In the real case, we do know, and the answer is yes. Exactly these operations are needed because of the real counterparts of the examples that I presented in a complex case, and they are enough to describe all real analytic functions locally definable from a given collection. But this is not actually a theorem about analytic functions. This is a theorem about smooth quasi-analytic germs, and in fact it is a corollary of a more general statement, and this takes us back to the beginning of the talk. So there's somehow there's a dichotomy in O-minimality in proving, in the O-minimal setting, the proofs of elimination results, quantifier elimination results, they either follow, well, one way to prove an elimination result is to reduce to the semi-algebraic case. So if you start with real analytic functions, how do you reduce to the semi-algebraic case? Well, if you have access to the complex extension of your real analytic functions, then it is essentially the Weierstrass preparation theorem that gives you this reduction. But if you do not have definable access to the complex extensions of your analytic functions, then what you do is resolution of singularities. And what you do actually works in quasi-analytic classes. So I will stop here.